If I could reincarnate tonight, I would be a Clorox wipe, 'cause I know in this climate you might.
In this last video of this lecture, we'll first talk about quotients of R modules, and then we'll talk about the isomorphism theorems for R modules. We need to talk about quotients first because several of the isomorphism theorems involve taking quotients. Okay, so an R module is an abelian group. And we know that any subgroup of an abelian group is automatically normal. So we can take the quotient of our abelian group giving our R module by the abelian group giving a submodule. And there's more to check, though, to see that the quotient of two R modules is an R module. Let's think about what happened for rings. When we discussed quotients of rings by subsets of the ring, for example, look at the discussion on page 241 of Dummett and Foote. When we took a quotient of the abelian group giving the ring by a subgroup, we needed a way to define a multiplication on the cosets that we got. So we needed some way to understand R plus I, the coset of our subgroup containing a ring element R, times S plus I, the coset of our subgroup containing the ring element S. And when you go, this is what led to the condition that our subgroup also had to be closed under multiplication by ring elements, which led to our discussion of ideals. But in this case, we don't need to multiply cosets when we take a quotient of R modules. We just need a way to define an action of the ring R on cosets. And it turns out that there's always a nice way to define an action of R on cosets using the action of R on the original R module M. And this is the content of proposition 3 of section 10.2, which says, let's say R is a ring, M is an R module, and N is an R submodule of M. We can always take the quotient of the abelian groups M and N, and that is a well-defined abelian group, but we need that quotient abelian group to be an R module. So the quotient of abelian groups M mod N can be made into an R module by defining this action of R. R dot X plus N is the coset of N containing R dot X. So the action of R on elements of M gives the action of R on this set of cosets. All right, so this has to be true for all X in R and all cosets X plus N in M mod N, where, okay, so what is this coset? This X here is an element of the R module M. All right, so given any R submodule, you can turn the quotient of abelian groups into an R module. Then when we talked about quotient groups and quotients of rings, we also would always talk about the natural projection homomorphism that we get. So here we have this natural projection homomorphism pi, which goes from M to the R module M mod N. So what does it do? It takes an element X in M to the coset of N containing X. And we know that this is a homomorphism of abelian groups, but it's also an R module homomorphism. And what is the kernel of this R module homomorphism? Well, the kernel of an R module homomorphism is the kernel of that R module homomorphism when you just think about it as a homomorphism of abelian groups. So once you believe that this is an R module homomorphism, it's clear that the kernel of pi is N, because that's what happens for the natural projection group homomorphism. Okay, so what do we actually need to check for the second part? Let me just say quickly. So, I mean, we know it's a homomorphism of abelian groups. So we just have to check that this homomorphism behaves nicely with respect to the action of R on M and the action of R on M mod N. So I won't give a full proof here, but let me give a proof sketch. So first, we need to check that this quotient of abelian groups really is an R module. And first, we just need to check that this definition of the action of R on this quotient makes sense, that it's well defined. So that is, if we pick different representatives for the same coset, let's say x plus n is the same coset as y plus n. So x and I are elements of this R module M, then it has to be true that the things they get sent to over here are the same. That it has to be true that the coset R dot x plus n is the same as the coset R dot y plus n. Okay, well, why is that true? Well, what does it mean for the coset x plus n to be the same as the coset y plus n? That means the difference of these elements in M, x minus y, is in n, is something that's actually in the submodule n, in the subgroup n. All right, well, we know, what do we know about n? It's not just a subgroup of the abelian group M, but it's an R submodule of M. So we have this element x minus y that's in n. And because this is a submodule, if we take the action of any ring element on this element, we stay in n. So R dot x minus y, that has to still be in n. But what is that? Well, this is R dot x minus R dot y. This is in n. But if R dot x minus R dot y is in n, then the coset of n containing R dot x is the same as the coset of n containing R dot y. Why is that? Because two things are in the same coset precisely when their difference lies in n. Okay, so that shows that this action of R on the cosets of M mod n is actually well defined, that it doesn't depend on a choice of representatives. But, I mean, that doesn't yet show that this action of R turns this abelian group into an R module. For that, there are a bunch of things that we need to check. So I'll pause and erase and say a little bit more about the proof here. Let's continue our discussion of the proof of this result. We've seen that this action of R on the set of cosets of M mod n is well defined. But we need to check that M mod n really is an R module with this action. So what do we have to check? We have to check all of the R module axioms. And this is a case where checking each individual R module axiom is pretty straightforward, but we really do have something to check. So just to give one example, we need it to be the case that the ring element R1 times R2 acting on the coset x plus n has to be the same as the ring element R1 acting on the ring element R2 acting on the coset x plus n. So if you just use the definition of this action, you'll see that this is true. But this really is something you need to check. And there are several other module axioms you need to check as well. So I encourage you to write down a full proof of this result. It'll be good practice in working with these types of statements about R modules. Okay, so let's talk about this last part. So we know that pi is a homomorphism of abelian groups with kernel n. But we need to check that it actually is an R module homomorphism. So what do we need to check? We just need to check the second thing that turns a map from M to between two R modules into an R module homomorphism. That is, we need to check that pi applied to R dot x is R dot pi of x for all R in the ring and x in the R module M. Well, let's just compare what the two sides of this are and hope that they're equal. What is pi of R dot x? Well, this is the coset of n containing R dot x. That's the definition of this natural projection homomorphism. And what is R dot pi of x? Well, pi of x is just the coset of n containing x. So what is this? It's R dot the coset x plus n. So what do we need to be true? We need r dot x plus n, this coset, to be the same as the coset r dot x plus n. But this is the definition of the action of r on m mod n. So you just write down what you want to be true. You look at each side individually, and then the fact that they're equal is exactly the definition of the action of this ring on this quotient of abelian groups. So there are some details to check down here, but what we've seen is that the situation for R modules is a little nicer than the situation for subrings and ideals. That whenever you have a ring, an R module, and an R submodule, the quotient turns into an R module, with the action of R being the simplest thing that you could think of, the action of R being here. Natural projection, which we know is a homomorphism of abelian groups, also is an R module homomorphism. And the kernel is what you would think it is. Yeah. So I'll pause and erase, and then I'll talk briefly about the isomorphism theorems for modules. In order to state the isomorphism theorems for R modules, we first need to define the sum of two R modules, because the sum plays a role in the statement of the second isomorphism theorem. So let's say that A and B are submodules of an R module M. What is the sum of A and B? Well, it's A plus B. It's the set of all things that are of the form little a plus little b, where little a is in A and little b is in B. And you should check that this really is a submodule of M. So the sum of two submodules is a submodule. We've already talked about the fact that the sum of two abelian groups here will be an abelian group. And you just have to check for this to be a submodule. Now you need this to be closed under the action of the ring on the module M. So it needs to be closed under the action of the ring. And once you believe that this is a submodule, it's clear that it's the smallest submodule of M containing A and B, in the sense that any submodule of M that contains A and B, well, it also has to contain all things of the form A plus B, because it has to be an abelian group. So it will contain the entire submodule A plus B. So now we're ready to state the isomorphism theorems for R modules. This is given as theorem 4 of section 10.2. The first one, let's say M and N are R modules, and phi from M to N is an R module homomorphism. Well, the first part is that the kernel of phi is a submodule of M. I've already mentioned that briefly, as it's one of the exercises in section 10.2 of Dummett and Foote. Kernel of phi is a submodule, and the quotient module M mod kernel of phi is isomorphic to the image of phi. Okay, so how do you prove this? Well, we know that phi is also a homomorphism of abelian groups. And if you think about this statement for abelian groups, we know why this is true. We have the isomorphism between the abelian groups M mod the kernel of phi and the image of phi. So we know a group isomorphism between the abelian groups on both sides of this isomorphism. But what we need here is that this is not just an isomorphism of abelian groups, but an isomorphism of R modules. So we need that this function that gives the isomorphism of abelian groups also is an R module homomorphism. So what do you need to do? You just do the same thing that you did to prove this for abelian groups, and then you show that the function that gives this isomorphism of abelian groups behaves nicely with respect to the action of the ring R on the R module M mod the kernel of phi and the R module image of phi. So what do? You do the same thing that you did for abelian groups, and then you need to check one additional thing about the action of R on the R modules on each side here. All right. The second isomorphism theorem. Let's say that A and B are submodules of the R module M. Then the quotient R module A plus B mod B is isomorphic to the quotient R module A mod A intersect B. Remember, this is this diamond isomorphism theorem where you draw this picture. We have this R module M, the submodule A plus B. A is in there, B is in there, and then we have A intersect B at the bottom. And it was an exercise that that I mentioned briefly, that the intersection of A and B is also an R submodule of M. And these lines, the dashed lines here, indicate where we're taking quotients and getting an isomorphism. So again, what do? You write down the map that gives you this isomorphism of abelian groups. And then you just have to check that that map is not just a group homomorphism, but it's also an R module homomorphism. So it's just like the previous one. You do the same thing you did for abelian groups, then you have to check that the map that you write down behaves well with respect to the action of R on the module on the left and the module on the right. The third isomorphism theorem, that's the one where you take a quotient of quotients, and it gives you a simpler looking module, or a simpler looking quotient that it's isomorphic to. So let's say M is an R module and A and B are submodules of M, where A is contained in B. Then the quotient M mod A mod B mod A, this quotient of R modules is isomorphic to the quotient of R modules M mod B. And again, same idea. We know that this is true for abelian groups. We have a function that gives an isomorphism between the abelian group on the left and the abelian group on the right. And now we'll need to show this also is an R module homomorphism. All right, I'll pause and erase, and I'll write down the last one, the lattice isomorphism theorem, which takes a little more space. Let's briefly discuss the lattice isomorphism theorem for R modules. Let's say N is a submodule of the R module M. There is a bijection between, on the one hand, submodules of M that contain N, and on the other hand, submodules of the quotient M mod N. How does this correspondence work? If you have a submodule A of M that contains N, what does it correspond to over here? This submodule A mod N of M mod N. And this correspondence commutes with the process of taking sums and intersections. We've seen something very, very similar for the lattice isomorphism theorem for groups and also for rings. So I'll say the proof here is the same idea as what I've been saying before. We know how this correspondence works, how it works for groups, in particular for abelian groups, and we just have to check that everything is compatible with the action of the ring R. So Dummett and Foote don't give details of the proofs here for any of the isomorphism theorems, and I won't either. They say exercise. But I've already pretty much said out loud in this lecture what the big idea is, that what you do is you copy what you've done for abelian groups, and then you check that the maps between abelian groups that you get are not just homomorphisms or isomorphisms of abelian groups, but they're also R module homomorphisms, that they are compatible with the action of R on the R modules on each side of your isomorphism.